Okay, so we will directly begin with the agenda. So today is the session 1 of the MATLAB practicals. We are learning how to program with MATLAB in order to solve the practicals that we are having in the course Sensoren für Fortgeschrittene. And let me also share my screen so you can see. Okay, cool. So, as I said before, the purpose of this session is actually concentration of the practicals that we are having in sensors course. And this session will be recorded for the ones that will want to participate later. In this practical, we are not going to show you any slides or something. We are going to work hands-on with the program, and I will suggest the same thing for you guys. If you want to learn something, not only in this case but also in other cases, you better work hands-on, and it's better if you really program and code yourself instead of just watching some videos, some courses and so on. You will learn the commands, but you will never learn how to use them if you just watch and not practice. You may ask questions while I am talking and teaching. You can directly turn on your microphones and interrupt and ask anything that you want, because otherwise you can forget them, and it's actually better if you ask your questions completely fresh. So first of all, I don't know which semesters you are. I suppose that every one of you have a MathWorks account with your university email address. In case you don't have any, you can go to MathWorks website and just register with your university email address. And if you register with your university email address, then you have the access, the license for the education version of MATLAB, and you can actually download the latest version from the website directly. So after that, you downloaded the whole program. You can log in with your, as you're installing the program, you can log in with your university account, and then you get the license and also the updates and so on. In MATLAB, we do have many and few toolboxes which are going to help us with different matters. I'm telling you this because I suppose you are a refresher, if not beginner, with the program. So the main thing with MATLAB program is actually that we don't need to reinvent the wheel, and we can actually use the toolboxes or predefined functions that are already there. For example, as instance, for calculating a Bode diagram or something, we don't need to calculate everything all over again, so we can use just the functions. And I will teach you how to learn to use the functions, not only a few functions, but also learn to actually find and use the functions that are already predefined. So with opening the program, we have actually a command window here, and then we have a workspace here. The command window is actually the window that we can enter our commands, and with pressing the enter they will be directly executed. And in the right side we have the workspace, or our memory and variables that we defined. So if we write any code here, for example, if we define something like a is equal 1, so you see that it is directly with pressing the enter executed, and then we have in workspace actually a column for the name, and we have the value of 1. We can also define different kinds of variables here, such as, for example, one of them is actually sims. We can define symbols like sims b, and as you can see here, now we have a symbol named b, and it doesn't have any value in it. And also we can use other types of variables like vectors and matrices. So as you can see here, we have a vector here named c with 2 columns and 1 row, and as you can see here, we can see also the value. If it's too large, we can click on it and then see it in variables. So as you can see here, we have it in a matrix form, just like Excel, and we have it right here. And if you want to define others, so I let it on your shoulders. You can work with the program a little bit, but we are going to directly learn how to program. So as you can see here, we do have a command window, but in this command window we are not going to do so much. So the best way to start with MATLAB is actually typing the edit, and then with pressing enter we come to editor of MATLAB. As you can see here, I have 3 sub-windows here. One of them is called Untitled. I'm going to start programming here. As you can see here, if I write a is equal 1, for example, and then press enter, it's not going to execute. Just it will be executed if I press on run. So we are going to write the program, hold down, and then write the program, hold down, and then run the program, and not directly work with the command window. So I'm gonna first start with my first program, and work with different functions and so on. So on top of every program of mine, I used to write CLC. What CLC does is actually clearing the command window, and then clear is gonna clear every last variable that we defined in our workspace. Why do we write them? Because we want to start over, and if we have any variables or something written on command window, we want to clear them before we execute the next, because it can cause some conflictions. So first CNC clear and close all. What close all does is actually closing all the other windows, such as figures, diagrams, and so on from MATLAB. So I personally prefer to write that in the first row of each of my programs. So if you click on run, you see we have to save that before we start. So I'm gonna save it named as app1. As you can see here, as I clicked on run, the command window is cleared with CLC and the workspace is cleared with clear. So what do we have next? Actually, the name of MATLAB is pretty interesting. MATLAB is short for Matrix Laboratory. That means that every variable that we define in MATLAB or in Workspace is going to be in form of matrices. That is the basics of MATLAB. And the other thing is actually when we want to address to different elements of a matrix or a general variable in MATLAB, we just have to use the index notations. What I mean with index notations, imagine that we define a matrix here, for example 1, 2, 3, and then 4, 5, 6, and then 7, 8, 9, and then I click on run. As you can see here, A is defined as a matrix here, 3 by 3 matrix, and if I want to address something such as exporting one of these elements, so for example this element, the 6th element, I have to just write the second row and the third column. And if I click here, you can see here that A is actually 6. So I do have a warning here, as you can see. Why? Because I didn't use any semicolons. If you use semicolons here, you won't see anything here in your command window, and you will see your variables just here. But if you leave off the semicolon, you are going to see the matrix directly here. So what do we have next? The next important item in MATLAB is actually using the operations. What I mean with operations is actually this. So as you can see here, if we have another matrix of, for example, again 2, 5, 8, and then 4, 5, 6, just an example, and then 7, 4, 1, and then if I define C is A multiplied by B, you can see here that actually C is going to calculate just like matrix multiplication. So the other thing is, if you remember the dyadic multiplication, if we want to multiply the element by element, we cannot use this star multiplication, and we need another thing. So if you're a refresher or new to MATLAB program, you may commonly have this problem, such as this. So as you can see here I have a vector or one row matrix, and here I do have a one row matrix, and then C is A multiplied by B. As you can see here, we receive an error. The reason behind that is actually because we cannot multiply a matrix which is 1 by 3 with a matrix which is again 1 by 3. It won't be easily possible, because this one with this one has to be the same. The problem is if we want to multiply this 1 with this first element of the B, we have to use the dyadic multiplication. And the dyadic multiplication in MATLAB is noted with dot star. if I run it again, then you can see that the first one is multiplied by the first one, the second one is multiplied by the second one, and the third one also. So it is pretty important, especially if you want to, as you will see later, with calculating the transfer functions and so on. It will be pretty necessary for you. So for another example is the windowing function. So if you have a signal like this, and then you have the Hanning window, for example, and you want to multiply them by each other, you just have to do it element by element, and you cannot. This signal is actually a vector, and this signal is actually this windowing is also a vector. So if you want to multiply them by each other, you need to use the dyadic or this dot star notation of multiplication. It is pretty important. So the next thing is that you always, I don't know, maybe you guys are already familiar with Python and so on, but the very important thing is that you write your code very understandable, because if not now, in the future you are going to have teammates, you are going to have other colleagues and so on, or professors or something. So the most important thing is that you code in a way that everyone understands, even you in next few years. You know, if you do it complicatedly, yeah, it can be that in next few years you will see your own code again, and you won't understand even a line of it, and it's pretty catastrophic now. So actually, what I mean with that, let's begin completely hands-on with a program. So I'm gonna define a vector named t, and then I'm gonna use linspace. So as you can see here, in newer versions of MATLAB, we do have this very cool feature that if we just type a few first letters of a command, the rest of it will be suggested by MATLAB itself. So I use this linspace because I want to define a vector which starts with 0, ends with yeah, let's say 100 pi, and then in 100, no, not 100, in 500 points. So as you can see here, now I do have a vector. I define a vector which is which does have 1 rows and 500 columns. If I double click on it, you will see that we defined actually our vector. So the next thing I'm going to do is actually defining an x, which is again, yeah, I can actually define linspace, but what I want to do is defining the sinus of the whole vector t. So what I'm going to do is actually writing sinus of t, semicolon. As you can see here, in x, I do calculated the sinus of the whole t vector. So the most important part is that if you want to have flexibility and change things in the future, you don't have to. You don't want to write your 500. If you want to change the resolution later, or you are programming for a length that you don't know already, you can predefine it as a parameter. So for example, you can write here 500 and write here n. So later you can just change it instead of changing, I don't know, maybe a few 500s in the code, and it can be that you don't find them anyway, any later. So it's better if you work actually with parameters, and for example, if you are defining a mechanical system and you do have an m, k, and c, the best way, I mean the mass, the spring constant, and the damping constant, the best way to do that is actually predefining it here as a parameter, and then write your program with the symbols and variables, and not numerics, but also the letters. It's going to be the best way. So that was another point, and the next point is actually if you are planning to submit anything for your professor in this course, it's not the case. We don't need any reports from your MATLAB programs or any copies or something. We don't need them. We just want to make sure that you do them, because you will be tested. You will have a quiz at the university, and actually you don't need to submit any reports, but I'm telling you this because of your own sake. So if you want to do comments, you can easily press tab a few times, and then you press this percentage symbol, and then right here, for example, defining the time vector. and then you can write here calculating this same, just like that. You can comment your own code. That is also yeah, pretty important. The next thing is talking about time domain, frequency domain, and Laplace transform. As a refresher, if you don't remember it from your bachelor, I'm going to talk a little bit about the time domain, frequency domain, Laplace transforms, and so on. So if you may remember, we do always have a mechanical system here, which is pretty simplified. We do have a damper, a spring, and a mass here. So if we do have this x direction and we do have this f, which is a function of t, we can actually write mx double dot plus cx dot plus kx is actually equal to f as a function of t. And if we do a Laplace transform, we get the m s in power of 2 plus c s plus k, and then a capital X of s is equal to f, a function of s. What actually Laplace transform does for us is bringing this equation of motion from time domain to the frequency domain. What this frequency domain help us is that we don't have any derivatives here, and actually our differential equation is converted to some kind of algebraic equation, and then it is really easier to solve that. As you can see here, if we want to calculate the x as a function of f, I mean dependent of f, we can easily use this notation, and then we know that x of s is going to be actually f of s, which is our input, and this x is going to be our output. So what I do is actually dividing the both sides by ms in power of 2 plus cs plus k. So now we didn't solve any differential equations. We just need to calculate. We just need to substitute the f of s here, and then we can calculate this, and then we can do the Laplace transfer inverse, and then we get our x of t. So here was a quick reminder of Laplace transform and the time domain and frequency domain, which is crucially important for us for the next of the session to know a better understanding of what it does. So this slide was actually about the mechanical systems and transfer functions. So what you can see here is actually as I said before, it is the output, and this one is the input. So transfer function is defined as output in frequency domain divided by input also in frequency domain. So the very important thing is you have to make sure that they are in frequency domain. So if you write it as easy as that, so transfer function is equal to out divided by input, which is a function of t, it is going to be wrong. Why? Because the very important thing is that we do calculate transfer function in frequency domain. So the next thing is that, which is pretty important in this course, and you probably know, is that if you do have a signal x, which is a function of t in the time, and the signal is like that, for example, what do we want to do is actually extracting the frequency components of this. And by frequency components, I mean if we do a Laplace transformation of this signal all over the time, we do realize that this is probably made of a few different frequency components. I will show you later what I mean, but for now, this x of s, we are going to have few frequency components which can actually be done by Fourier transformation, FFT, DFT, or others. In this practical, we are going to focus on FFT. So let's have a better understanding from this. So what I'm going to do is actually combining a few signals with each other. As you can see here, this one is x1, So this one is going to be sinus of t, and the next one is going to be 3 times sinus of 4 times of t, and then I'm going to to summarize them together, plus x3, and then click on run. So as you can see here, I do have an x, which is a combination of these 3 signals, which each of them have their own amplitude. Here is 1, here is also 1, but here is 3, and here is actually 4 times t and 2.5 times t. So they are actually different in frequencies as well. So what we are going to do now is plotting these to have a better understanding of this. So I'm going to open a new figure. Actually, we don't need that, figure is enough. So open a new figure, and then I'm going to write plot. With plot we do have x as a, no, excuse me, in plot we do have to enter what comes here first, and then what comes here. So t and x. If I click on run now, you can see this is actually our signal. So this signal is actually not very easy to read. Yes, you can understand that. Let me take a photograph of this. So it is right, maybe you can see with your bare eye that here we do have a signal in this area, and here also with these peaks we do have a signal, and here as well we do have a signal. But the main thing is you cannot identify them anymore, especially if you don't define them by hand and you receive this information from a sensor. So what do we want to do is actually doing an FFT and see what kind of different frequency component do we have here. So I'm gonna suggest you something, and that is using the help of MATLAB. The application MATLAB does have a very strong documentation, which with examples and so on, unlike any other applications that you used, such as Python and so on. So as you can see here, I can easily enter FFT here, click on enter, and then the documentation of MATLAB is going to open for me. And as you can see here, we do have a documentation of mathematics, Fourier analysis and filtering. Here are all the different toolboxes of MATLAB. You may see one function which is common between different toolboxes of MATLAB. So as you can see, we can click here and we can see how to use this predefined function, FFT in this case. So as you can see here, we do have an example also here for us. So as you can see, here is the signal itself, x as a function of t, which is through the time defined, and then we do have FFT. So what the FFT does is actually bringing a whole vector into the frequency domain. Once again, if we look at this, so as you can see here, this Laplace transform helps us to actually bring actually an equation of motion, a differential equation to Laplace to frequency domain. But what we do have here is actually no relation or equation of motion or something. It's just numbers and yeah, just data, just raw data. So as you can see here, with FFT we can bring the information of a sensor from time domain to frequency domain. So we are going to do that, and I'm going to write x capital is equal FFT x, and then I'm going to actually, let me open 2 subplots here. What subplot does is actually splitting the whole figure in different diagrams, so you can draw 2 diagrams on one figure. I'm going to show you right now. So as you can see here, I can write 1 by 2, the first part. Actually, let us do the opposite way. And then we can open new subplot, and then we can write here 2 by 1, and the second part. In the second part, I'm going to plot this x. So if you click on run, actually that is wrong, because t is equal, let us proceed, then I will explain. So as you can see here, here we do have the signal itself through the time, and here we do have the peaks. As you can see here, we have 3 main peaks. One of them is here, one of them is here, and one of them, the other one, is here. Exactly the same thing that we expected, because we defined the input of the FFT function by ourselves, and we knew actually that we do have 3 frequency components, 1t, 2.5 times t, and 4 times t. So as you can see here, we do have 3 peaks here, or 3 frequency components. The main thing with FFT is that we actually just need the half of it, and the rest we can throw away. And the second thing is that, as you can see here, I plotted the x capital, or the result of the FFT through the time. It is actually false. We need to plot it through the frequency, but I didn't do that, and it is actually false. So, but the main thing I wanted to show you is that we can bring any signal, any vector of signals to the frequency domain, and then look at it if it's which frequency components does it include. So the next thing we are going to discuss, and pretty crucial, and it is pretty crucial for your practicals, is working with magnitude and phase. As we told before, we are engineers of mechatronics. We are concentrating on usage of different sensors and so on. So hence is actually Bode diagrams pretty familiar for us, and we will be needed to use them as well. So I'm going to explain a little bit about magnitudes and phase of Bode diagrams. So as you may know, actually let me copy these parts and bring them here. And I cannot make them any, yeah, okay, no problem. So, as you may know, here in frequency domain, the main thing with x is that we calculated it as x of t. So the main thing is, in time domain, is actually important for us how the behavior of x through the time is. But here in frequency domain, on the contrary, the most important thing for us is actually how this x capital as a function of s, or as a function of j omega, works. So as you can see here in frequency domain, we don't have our x as a function of time. In other words, how the behavior of x through the time changes is not very important for us, but actually it is important how the changings of x through the frequency changes. Let me tell you an example. So imagine that you own a car, and you are driving on a surface which is not very flat and does have potholes and so on it. So the main thing is, through the time you are going to work every day, and you do have a pothole in the way, which is between your home and your working office, and every goddamn day you will run through these potholes, and through the time you gain the experience of how it works. So if sometimes you drive with 30 kilometers per hour, sometimes you drive 50 kilometers per hour, and sometimes you drive with 80 kilometers per hour, and through the time you will get it that in higher speeds, or yeah, like 100 kilometers or something per hour, it's gonna actually not shake your car at all. That's an example of how the behavior of x, the deflection in this case, is actually important for us through the frequency and not time anymore. In other words, the response of the system, or this x, the deflection of the mechanical system, the deflection of the mechanical system will be changing, will be altered through the different frequencies. And that is what is called the magnitude. So the magnitude through the frequencies, can be different, but in this case is actually going to be like this, with a slope of 40 decibels per decade. We are going to see it right now, but just wanted to make a refresher about the magnitude and phase, and what these time and frequency domains are actually about, and why are these Bode diagrams actually very important for us. So why is it here 40 decibels per decade? Does anyone know or remember from the bachelor degree? Can anyone respond to that? Guys, some interaction here. So the main thing is these Bode diagrams are actually not in not in numerical scales, not in decibel scales, but they are actually in decades. What that means is actually if we draw the Bode diagrams, the magnitude diagrams, the magnitude of a signal here with so first of all, zero, we don't have any zero. So okay, let's say here is 1, 2, 3, 4, 5, 6, and the 10. Actually, we are not going to see anything. What happens is actually this changing of the magnitude is so low that we cannot notice it if we use the normal scale. I mean 1, 2, 3, 4, 5. What we are going to use is actually 10 in the power of 1, 10 in the power of 2, 10 in the power of 3, 10 in the power of 4, and so on. 10 in the power of 10. And now, since we changed the scale from the linear scale to logarithmic scale, now we can see the changes very quickly, right? So in the first type of systems, which we do have a transfer function like, let's say 1 s plus 1, this slope is going to be minus 20 decibels per decade. And with decade, I mean the difference between 10 in power of 4 and 10 in power of 5, or 10 in power of 3 and 10 in power of 4. So as you can see here, and here, if we do have here minus 20 decibels, it is going to be a system of degree 1. But if we do have a system which is like this, which is like this, and we do have here minus 40 decibels, and here is, for example, 10 in power of 2, and here is 10 in power of 3. What we do have here is actually transfer function of, for example, s2 plus 3s plus 2, which has a slope of minus 40 decibels per decade. So let's go to MATLAB again and hands-on and work on it to see how it works. So let's define let's open another app and work and start all over. So CLC, clear and close all. Or no, let's work actually on this. It's gonna be better for us, I suppose. Let me check again. No, actually, let's open a new code. Save it on the name of CLC clear close all. Save it on the name of F2, and define a real transfer function. So in MATLAB, you can define different types of systems. One of them is SS, or state space, but here we are going to use the transfer function. The normal transfer function is going to be defined as that, so we can define sims, or let's say I'm going to define a system which is called sys1 is equal to TF. Let's take a look of transfer function. So exactly, as you can see here, in transfer function we have to give the numerator as the first input, as the first argument of the predefined function, transfer function, and then the denominator here. So as you can see here, I can give 1, so let's say 1, and then 1 and 2, 1 and 1, let's say. So as you can see here, system 1 is defined just like this. So the first one is 1, and here is 1 and 1. So if I add another 1 here and a 0 here, you can see it's going to be like this, the second order system. But let's start with this one. But actually, as you can see here, this formation of the transfer function, I don't like it at all. So it's not really easy, because it's going to be eventually very difficult to use. What I personally prefer is defining an S like this, and then transfer function 1, no, actually transfer function S, I suppose, or transfer function 1, I cannot remember anymore. Yeah, transfer function 1. Or actually 0 and 1. Nope. I think it's 1. And let's say sys1 is equal to S divided by S plus 1. No, this one doesn't work, unfortunately. Let's say 0 and 1 and 1. No, 1 and 0 and 1. Yeah, exactly. So what I rather do is actually using this command. So I predefine the S as a transfer function, which is a normal S, just a single S. And then from now on, I may define everything that I want instead of using this transfer function, which is actually not very user-friendly with this numerator, denominator, and so on. I can easily write, for example, system is S divided by S in power of 2 plus 3S plus 3S plus 1, for example, or 2. It's going to be really, really easier instead of using the transfer function itself. So if you ever want to define a transfer function, I suggest this. So you design the S first, and then you use this. You cannot actually use this sims S. You cannot use this command, because then the type of the value of the transfer of your variable is not going to be a transfer function. As you can see here, the type of this variable S is a transfer function. But actually, if I ignore this, as you can see here, the system is not a transfer function anymore. It's just a symbol. It's just a symbolic expression. So you cannot use this, and you have to define your S as a transfer function. So let's start with Bode diagrams. So as you can see here, we do have actually, let's refer to documentation of Bode. Yep. Bode. Yeah, exactly. As you can see here, we do have a predefined function in MATLAB, which is in signal processing toolbox, I suppose. And then we don't need to calculate anything by hand. I mean, the magnitude and the phase and so on. We just need to enter any kind of system like a state space or transfer function in it, and then we will get the Bode diagrams both in magnitude and phase. So as you can see here, I can write Bode is equal to, actually I don't need to save it anywhere, so just Bode, and toss the sys inside of it. And as you can see here, we do get the Bode diagram. So as you can see here the magnitude is on decibel, which is 20 times of logarithms of the magnitude itself. And then on the x-axis we do have the frequency, which is in decades. We can actually do another thing to make it more beautiful, and we can say grid on. If I click again, as you can see here, the grid is also on. And we do have two subplots. The first one is the magnitude and the second one is the phase. As you can see here, we do have a second order system, the first order system, which actually the phase is from 90 to minus 90, or yeah. And as you can see here, we do have a slope of minus 20 decades, minus 20 decibel per decade. So this one was a simple example of how we show a Bode diagram. But the thing is, this Bode diagram only responds and accepts the argument if it's a transfer function, if it's a symbolic transfer function. But in other words, only if we have this, and it won't work if we have this. The Bode diagrams are not going to work on the data that we have, so we have to actually calculate the magnitude and the phase ourselves, I mean manually, and therefore it is really cool to know this Bode command. But the thing is, it's not going to work if we are going to work on the data that we have already there. So let me check my notes. So as you may know, the result of an FFT can be actually complex numbers. But here we don't have any complex numbers, unfortunately. We don't have any complex numbers, but it doesn't matter. I'm just going to show you how to calculate the magnitude and phase. So the main thing is, by calculating the magnitude and phase manually, the problems we are facing is that we cannot use the Bode diagram anymore, and we just have to calculate the magnitude ourselves. And calculating the magnitude is actually what we have to do. Oh, let me. Okay. So if we want to calculate the Bode diagram ourselves, what we have to do is actually, here's magnitude, and here is the frequency or the omega. So what we have to do is actually exciting the system with all these frequencies which are here, with different, so we can see the magnitude. And actually this line that you are seeing here is not going to be that continuous, and we have to calculate each point ourselves. But as I told you before, the main thing is we don't have to do these calculations in linear scale, like 1, 2, 3, 4, 5 till 10, but actually we do need to calculate it in logarithm scale. So what we want to do is actually, for example, here is 10 minus 2, which is actually kind of 1, and here is, no, sorry, this is actually kind of 0, and here is minus 1, and here is 10 minus 10, 0, and then here 10, 1, and then here 10, 2. what we are going to do is actually selecting different points here in not linear scale, but also in logarithm scale, and then we will calculate this this magnitude or the absolute value of of the signal in each of these frequencies, and then we will plot this diagram together. So so how we can convolute this, let me think. Okay, I can't find my notes right now, so we postpone this this calculation of Bode diagrams, manual calculation of Bode diagrams to the next session. So let's proceed with the next step, and that will be the figures and the plots. We already talked about them. The next thing is actually saving the workspace, and you're reloading the workspace. Sometimes we write a really long code, which the first few lines or the first sections are going to have a huge impact on our calculation capacity of the system. So I mean, imagine that you wrote a code which is actually 100 lines, and the 20 first lines are going to cost us a few minutes or a few hours. So and every time we run the program, we do run CLC clear and close all, and this CLC clear and close all are going to ruin everything that we had here. So what is clever to do and what we can do is actually saving. Let me run this part again. So imagine that here we have calculated instead of 500 elements, we have calculated like 50,000 elements, and this every time to calculate this 50,000 is going to cost us like a few hours, and it is really clever to save the workspace somewhere and then reload it again. How it's done is actually like that. You can first run the first section, which is really time costly, and then you can right click and click on save, and then you can see that you can save the whole workspace or the whole variables that it defined in that you calculated and defined in workspace. You can save them with a mat file. You can save them here under data, for example, and click on save. And as you can see here, we do have data.math, and if we double click on it, let me clear the workspace here, and if I double click on it, nothing happens. Nice. Yeah. X. Why aren't they here included? Yeah, it is really embarrassing. So Yeah, because I have it open here. So yes, as you can see here, these variables that we defined and calculated and saved here in data.math are already once again here listed. And what that means is actually we can, instead of calculating the whole thing again, once again, so imagine here are the first 20 rows which are really slowing the whole system. We can actually right click and comment them, and from now on that we calculated it just once, we can write here load, and then as you can see here, load data.mat. And now if I click on run, you can see that we have them already here. So the main thing is, if you have a part of the program which is not that fast and it is pretty slow, what you can do is actually saving your data that won't change. So it can be that you want to change this 500 again, or I don't know, maybe till here, and here before FFT you want to add something else, I don't know. But the part that doesn't change anymore, you can save the results of that part and then load it again instead of just calculating it all over again. So here's a quick tip for you as well. What else do we have on today's agenda? Help and documentation, and a little bit about loops. So just like other programming languages, we do have also different types of loops here. For example, for loop. So in for loop you can write for I is 1 to 10, and here another for j is 1 to 20, or as I said before, the best way to do this is actually nothing like that, but you can write here to A and here to B, and then you can define something like this. You can write A is equal to zeros. If you want to calculate anything that if you want to calculate each element of a matrix here, the best way to do that is actually write actually predefine and initialize a variable for that, and the best way to do that is actually a zeros matrix. The zeros matrix is going to be like this, so you can see with the size the size of A and B. A is going to be the number of the rows, and B is going to be the number of the columns, and then you can parameterize it as I told you before here. So you can tell okay, now A is 10 and B is 20, and now A is going to be 10 by 20 matrix, and then for each element we are going to calculate this. So I'm going to write A, the first element is I and the second element is J, and now is going to be I, J. And now end for the first 4 and then end for the second 4. And if I click on run right now, we don't need this actually. So A is going to, as you can see, is a 10 by 20 double type. And as you can see here, we do have multiplication. As you can see here, 1 by 1, 2 by 1, and then 2 by 3, and then 4 by 4. And as you can see, we calculated this. So these fours and the different types of loops are also included in MATLAB, and you can use them as easy as that. As the next, but the main thing is that the variable you are using for the for has to be integer, so you cannot easily write for I is a member of this T, for example, because here we don't have integers, but this has to be an integer. We do have also while, switch case, and so on. You can see them, but for this practicals, as we said before, we are concentrating on this practical. So for this practical, we actually just need for. Nevertheless, I have to say that for some kinds of calculations, as we talked before, for example, for the dyadic multiplication or sinus and so on, we don't need to use for. For example, here you can see that with t vector, we do have 500 elements, but calculation of x1, which is a sinus of t, doesn't require a for, and you can easily toss t in it. And for other, for different types of multiplications, just like the dyadic multiplication, as I told you before. So if we have A is equal 1, 2, 3, and then we have B is equal 4, 5, 6, and we want to do a dyadic multiplication. We don't need to actually use a for loop. We can easily write dot star b, and it will be calculated. So the main thing is don't use the loops as far as you can, because some of these loops aren't necessary. But if you have to, like a convolution multiplication or something, you can use for. But try not to use these loops, because these loops can make the program so heavy and slow. So the next thing I wanted to talk to you about before closing the session is actually the windowing. I wanted to show you also an example here, but it doesn't seem to work, unfortunately. I don't know why. But I'm going to talk about this and solve the matter for the next session, so the next Friday. Another very important thing beside the Nyquist-Shannon theorem here in this course, actually what you have to really learn well for the practicals is first the sampling theorem. I'm going to explain it here, and then the truncation leakage. Probably we are going to repeat them next week as well. So, but in sampling theorem, as you may know, if we do have a signal like this, which does have a frequency of 2 pi, for example, or no, 2 hertz. Actually, what do we have to do? So here is 2, and here is 4, and here is 6, and here is 10. So what we have to do is actually setting the sampling frequency at least 2 times larger than this. Why? Because if we sample with a frequency of 4, we are going to see this part and this part, and we are going to see this part and this part, and hence we are going to just identify the peaks of this. And if not using this frequency sample at least 2 times larger than this, we are going to not satisfy the Nyquist-Shannon theorem, and that means we are going to have the aliasing problem. This one we also going to see next week. You know that already, but the thing I suppose you don't know already, or you just heard in this semester, is actually this truncation leakage. So the problem with truncation leakage is that imagine that you have a signal like this, and then imagine that you have a signal like this. Why doesn't it work? Imagine that you have a signal like this, and then you decide to cut it like here, and then use this part for your FFT. So what happens is actually, if you trunk it here, what happens is that we started with 0 and we ended with, I don't know, maybe -1 or something. And what happens is actually here and here, since they have a difference, so what FFT sees is actually a difference here, and this difference is like the next signal is started here. So if we copy this signal, this exact signal, over again here, you can see here that in FFT point of view, we do have a little bit of Dirac delta function here, because we do have an instant jump here, and this instance of jump is gonna cost us in all frequencies. So you know that if we do have a delta Dirac here, just here is x, here is t, here is x, and we do have a delta Dirac here, it's going to show itself in all frequencies. If you do the FFT of this, you are going to see something like this. So it's going to affect all of your frequencies. In other words, this instant impulse is going to show itself in all frequencies. In all frequencies. And why? Because it's like it's like an step. It's like a step signal with frequency with an unlimited frequency, right? So we are going to see it in all frequencies. So the main thing, the main thing here with the truncation leakage is that what we have here, this difference between the cutted part, this end part, and this start part again. So this is going to be seen just like a Dirac impulse. A Dirac impulse, and it's going to affect all across this. So what we are going to see is actually one signal here, one pulse here, which is the frequency of this sinusoidal signal, and then something like this all over, like a mountainside. And this is what's called leakage, truncation because of this, and leakage because of these parts. So what we can do to reduce this truncation is actually using a windowing function. This windowing function what the windowing function does is actually multiplying the raw signal with a signal like this. Oh, sorry, it's supposed to end here. It's multiplying this by this, multiplying the original signal with this windowing signal, which will reduce. So as you can see here, here is 0, here is nearly 0, and it's going to reduce this part like this and reduce this part like this, and hence the truncation will be really, really lower. So here it's going to be 0, so this difference will not exist anymore. And this is the application of windowing, which we are going to use next week. So I'm going to close this session here. It is already 1 hour 15 minutes. It is too much. Thank you for your participation. And next week, this exact same day and same hour, we are going to work with Simulink. Get a little bit familiar with Simulink, and then show you the windowing and Bode diagrams, how to calculate them manually and not using the predefined functions of Meta. So thank you for your participations, and see you next week.